Hi, we are going to cover one sample t-test in this video. And if you remember, one of the assumptions underlying the one sample t-test is that the variable that we're dealing with, the sample data is normally distributed. So we're gonna, we have a data set of SAT scores from Judson freshman a few years ago, and we're going to compare the average SAT score for Judson freshman to the state average in that year. But first, we're going to explore the data and just see if there's if the data are normally distributed. The easiest way to do that, there are a number of ways. One, probably the easiest way to do that is through an analysis set called Explore. And so we find that under Analyze, Descriptive Statistics, and Explore. And so Analyze, Descriptives, and Explore. And that brings up a dialog where SAT is our variable. We're going to move that over to the dependent list. If later on we'll have a independent sample t-test to look at, and there we'll have put our independent variable in the factor list. But right now we just have a dependent variable in SAT. And I'm also going to go over to the plots dialog, and I'm going to request a histogram and normality plots with tests. Okay, so that will allow us to examine whether the normality assumption is met or not. So I'm going to continue and say okay. And this is the output file that we get with the Explore analysis. So we get quite a few different tables and graphs. The first table is just tells us the number of valid cases that we have. So it's case processing summary table. Number of valid cases we have, 110. 110 students with SAT scores. The number of missing cases and the number of total cases. So there's no missing cases in this for this variable. The second table gives us our measures of central tendency and variation. Okay, so there's a couple of unique features about the descriptives we get under the Explore analysis. So we get the mean score. So the SAT average for our sample is 1044.09. We also get a confidence interval, a 95% confidence interval around this mean. And this basically says if we had measured all Judson freshmen of this particular year, the actual average SAT score was expected to be between 1,008 and 1,079. Okay, so this just accounts for sampling error. This is our estimate of what Judson freshmen earn on the SAT, but there's some sampling error with that because this particular group of people may be different than the typical Judson incoming class. So the typical Judson incoming class could be expected to have a score between these two data points, the lower bound and the upper bound estimate. The 5% trim mean gets its name by trimming off the ends of the high end of the distribution and the low end of the distribution. So 5% of the cases on the high end for SAT and on the low end for SAT are lopped off here. And that's to control for any outliers. So if there are outliers, the mean and trim mean will be different, quite a bit different but they're very close to each other in this case, indicating that there's not any outliers in our data set. The median, we also get the median, and then the variance, standard deviation, range. We get the interquartile range, which takes the 75th percentile minus the 25th percentile. So this is kind of the middle 50% of cases. And it says, the interquartile range is 265. So the person who scored at the 75th percentile scored 265 points ahead of the person who scored at the 25th percentile. That's a pretty narrow range for this test. Finally, we get two statistics that tell us about the distribution shape. So we get a skewness statistic of 0.14 and a kurtosis statistic of negative 0.66. So there's a couple of things to note about the skewness and kurtosis statistics. First of all, the sign tells you which direction the skew is in. Thankfully, a positive skew statistic indicates a positively skewed distribution. Okay, so we have a coefficient of 0.14, and that's positive. So we can say there's a little bit of, at least a little bit of positive lean to the distribution. For that to be meaningful, however, one rule of thumb. So again, here there's not sort of a set way to interpret significant skew, or but one way is to compare the skew statistic to its standard error. And if the skew statistic is 3 times more than the standard error, its standard error, then we can say that it's significantly skewed. Okay, in this case, it's less than 1. So there's no skew to be worried about. Kurtosis, the negative and the positive signs for kurtosis indicate the amount of peakedness or flatness. A negative coefficient indicates a flat distribution, a platykurtic distribution. A positive number indicates a peaked distribution or a leptokurtic distribution. But again, for this coefficient to be meaningful, it really needs to be about 3 times as larger than its standard error. And here, it's a little over, the absolute value of the statistic is a little over 1 times the standard error. So nothing much to worry about there. So just from this descriptives table, we can kind of see, okay, the mean and the trim mean are about the same. That indicates there's no outliers. And the skew and kurtosis statistics don't indicate anything abnormal. So just by looking at these data, we can probably say, yeah, the distribution is probably normal. There is a formal test of normality, however, and that's referred to as the Kolmogorov-Smirnov test. And there are a few statistics out there that do this. Shapiro-Wilk is another one. The one I like to use is the Kolmogorov-Smirnov or the KS test. Okay, and this test is a test. It tests whether the observed distribution down here, graph down here in the histogram, departs significantly from a normal distribution. If it does, then the test statistic with a given number of degrees of freedom is going to have a p-value or a significance value of less than 0.05. Okay, this p-value or significance value is 0.20, so it's above 0.05, and therefore it's not significant. And we would say our distribution is not significantly different than normal. Okay, so the assumption underlying the one sample t-test appears to be satisfied in this case. If we continue down and look at the histogram, that confirms it. It's a pretty normal looking distribution with lower frequencies on the extreme left and the extreme right. In most of the frequencies, most of the observations right in the middle of the distribution. We also get a few other useful plots with this. So again, Explore gives you a ton of data to look at. This is a stem and leaf plot. It's another type of frequency distribution. It also shows you the shape of the distribution. It does it on its side. So however far out the leaf goes here is how high the bar extends in a histogram. Okay, so it's sort of an inverted histogram. But the nice thing here is that you can see the individual values in the distribution. So the first column, we have a frequency column. This is the number of times that a particular number of observations in each row. So the first row is 1 observation. The second row is 6, etc. The nice thing, so the stem and the leaf, it gets its name. So the stem is the first digit or the first 2 digits behind the decimal, ahead of the decimal, to the left of the decimal. And these are values in the hundreds. So the first value represents hundreds. So the first value is a 6, that's 600. And then the second value, the values on the right side indicate the tens, okay? So this value is 80, 8 tens. So putting those two together, there's one score of 680, okay? You have the frequency of 1, and we put these two together at 680. If we go down a line, we see that we're starting with 7, so 700. And we have 2 zeros. So there's that translates to 2 700s SAT score, 2 separate ones. Then we have a 1, so we have a 710. We have 2 3s, so a 730 and another 730. And then we have a 740. Okay. And that we can continue on. So 750, 770, 270, another 770, and so on. So this can be another useful plot to look at your data. Then we get a couple of plots that are a little bit more like art forms to look at. So this is another way to evaluate the normality of our data distribution. The diagonal line, the line on the 45-degree diagonal, represents a normal distribution. This is how the distribution should look in this particular layout. The dots represent the observed values. So the closer the dots are to this diagonal line, the more likely it is that our distribution is normal. Okay. Typically, these dots stay pretty close to that line. So it's pretty clear case that our distribution is normal. But that's not always the case. Sometimes you have some what looks like significant departures from that line. But it comes down to having experience looking at these plots. And like I said, it's more of an art form. The more reliable way to assess this, again, is the KS test, the commodity string test. So that's what I prefer to look at. This is a detrended version of this QQ plot. So here, this diagonal line is flattened out, and it's put on a horizontal axis, and our observations lie above and below it. Okay, so again, we want the observations to remain as close to the horizontal line as we can. Here it looks like there's a little more departure, but again, our test said no, it's we have a normal distribution. The last output we get is a box plot. And if you remember from earlier in the course, a box plot gives us several data points. So the line in the middle of the blue box, it represents the median. The top and the bottom of the box represent the 75th and the 25th percentile, so the interquartile range. So you can kind of see, okay, interquartile range ranges from just below 1,000 to maybe close to 1,200. And then the whiskers on either side represent the whiskers represent the last value that's not wouldn't be considered an outlier. Any observations that are outliers would be sticking out on the other side of the whiskers. Okay. So that is an overview of the Explorer output. And again, our assumption of that the SAT scores are normally distributed is satisfied, so we can proceed with the one sample t-test. For the one sample t-test, we are going to analyze. So we can run this from the output or back to the data file if we want. I'm going to go to analyze and compare means and proportions. That's what my dialog looks like. If you have a different version, and the options may look slightly different, but should be something very similar. Compare means, proportion, and then I want to find the one sample t-test. Okay, so analyze, compare means, and one sample t-test. From there, I'm going to throw the SAT variable to the test variable box. And right now it's the default test value is 0. The test value is the population mean or the standard or the criteria that you want to compare your sample mean to. Okay, so the one sample t-test compares your sample mean to some population mean or a standard or a criterion. For Illinois SAT test takers in the year in which our data were collected, the average for Illinois students was an SAT score of 1007. So that's what I'm going to enter for the test value. And so that's the value it's going to be compared against my sample mean. Okay. So once I have that, I can say, okay, I can run the analysis. Okay, and we get a little bit of an output. We get the initial table that has some of our sample summary statistics in it. So you have 110 observations, 110 students with a sample mean of 1,044. We knew that from the descriptive analysis. Have our standard deviation and the standard error. The next table is our one sample t-test table. Okay, so here the t-value comes out to 2.087 with degrees of freedom 109. Degrees of freedom for one sample t-test again is n-1, so we have 110 observations minus 1 because we're trying to estimate one population parameter. And then the significance, our p-value, we're going to use the two-sided p-value in this particular case because we didn't have a good idea if our sample mean would be higher than or lower than the state population average before we collected data. Okay, obviously we know that now. If we had an idea, if we expected our sample to have a higher mean or a lower mean, then we could have chosen the one-sided p-value, but we're using a two-sided p-value. So again, the criterion for determining statistical significance is that the p-value is less than 0.05, and in this case, it is 0.039, so that is less than 0.05, and we can say that our t-value is statistically significant, indicating that the sample mean for Judson students is, in this case, 1,044 is higher than the sample mean of 1,000, the population mean of 1,007. So our Judson students perform significantly better on the SAT than the state average in this particular year. Finally, we have our estimate of effect size in the last table. And we're going to stick with Cohen's d for our t-test. So we're going to go to the point estimate column, and that indicates that Cohen's d is equal to 0.199. Okay. In the slide deck, I communicated that a small effect size is equal to 0.2, a moderate effect size is equal to 0.5, and a large effect size is equal to 0.8, according to Jacob Cohen's standards. So this particular value is closest to 0.2, which is our small effect size. So we have a statistically significant difference between Judson students who scored an average of 1044 on the SAT and the state population average SAT score of 1007. The effect size, the difference between these two groups was small, according to Cohen's D. And that is that for one sample t-test.